Before there were dreams, before there were eyelids to close or beds to curl into, life was already learning how to rest. Hello there, and welcome to the Late Night Scientist channel. Tonight, we'll travel across billions of years, through ancient oceans, early nervous systems, drifting fish, cautious reptiles, dreaming mammals, and finally, the restless minds of humans, to uncover how sleep itself evolved. It's a quiet, winding story of survival, imagination, and the strange brilliance of shutting down to stay alive. So settle in, breathe slowly, and let the long history of sleep carry you toward your own. In the beginning, so far back in time that continents had not yet gathered the courage to exist, the oceans were warm, mineral-rich, and profoundly busy in the way only early chemistry can be. The world was not quiet, not peaceful, not still. It was a restless cauldron of reactions, a place where life was inventing itself one fragile molecule at a time. And within these prehistoric waters drifted the planet's earliest organisms, simple, delicate, astonishingly small, and yet unknowingly on the verge of discovering one of biology's greatest secrets: rest. These organisms had no eyes to see the waves of brightness and shadow that washed over them each day as the planet turned. They had no neurons to process information, no idea of what a risk or a decision or even a moment was. They simply existed, tiny islands of chemistry, maintaining themselves against the dissolving power of the sea. And yet something curious was already happening inside them. Their metabolisms, those early engines of energy, were not constant. They hummed and quieted in regular rhythms, rising when the light returned and falling when darkness came. This wasn't sleep, not yet. But it was the very first hint that life, even in its simplest form, benefits from ebb and flow, from doing a great deal when conditions are favorable and very little when they are not. Life, it seems, had begun practicing the art of rest long before it had the machinery to truly fall asleep. The earliest cells relied on light as a kind of distant, cosmic metronome. When sunlight bathed the waters, photosynthetic organisms unfurled their chemical pathways, capturing energy with the enthusiasm of creatures who had no other way to eat. But when the light faded, these same organisms downshifted, letting their systems idle at a slow, economical crawl. It wasn't a deliberate choice. Nothing with this level of simplicity could choose anything, but rather a natural result of limited energy. Darkness made life harder, so life responded by doing less. Over millions of years, these day-night cycles sank deeper into biology. Chemical reactions that happened faster in light and slower in dark became linked, then synchronized, then inherited. By the time early microbial mats formed across shallow seas, entire communities of organisms were rising and resting together in a quiet, almost musical choreography. Each cell was still mindless, but collectively they pulsed with a rhythm older than any lineage, older even than the idea of rest itself. The benefit, though unrecognized by the organisms experiencing it, was profound. When these cells slowed at night, they produced fewer damaging byproducts. They reduced strain on fragile membranes and enzymes. They conserved energy for the more productive hours to come. In a world dominated by chance, this small habit, this subtle pattern of activity and stillness, gave life just a bit more stability. The first biological rhythm had begun, and with it, the seeds of sleep. Imagine one of these ancient cells, suspended in warm, murky water. It divides occasionally, drifts aimlessly, and measures time not with thought, but with chemistry. Each sunrise, its molecular machinery brightens like delicate lanterns flickering to life. Each sunset, they dim. There is no awareness in this cycle, no experience, but still, something about it feels familiar. The lineage of every creature that has ever curled up, closed its eyes, and drifted into dreams passes through this tiny, drifting ancestor. It is the quiet beginning of a story that will one day include REM waves, tangled forests filled with dreaming mammals, birds sleeping with half a brain awake, and humans lying awake insisting they are definitely going to fall asleep soon. But all of that is far in the future. For now, the story is simple. Life works better when it rests in predictable patterns. It survives longer. It grows faster. It makes fewer mistakes. And evolution, never one to ignore a useful pattern, begins reinforcing these rhythms until they become fundamental to biology itself. There is a gentle poetry to this early world. The planet spins, the light cycles, and the smallest living things sway in the dark, like fragile lanterns waiting for dawn. In their vulnerable simplicity, they mirror something that would remain true through billions of years. Rest is not an indulgence, but a strategy. A way for life to pause, repair, and gather itself for another round of existing. A moment of strategic loafing, if you will, though none of these cells would ever admit to such laziness, mostly because they are composed of exactly zero pride. What makes this era so extraordinary is how unintentional it all is. There is no predator to hide from, no brain to restore, no memory to consolidate. Rest is not solving a problem. It is simply happening. It is a natural outcome carved into life by the spinning of the earth itself. Sleep, in all its later complexity, will eventually grow from this seed. A humble metabolic rhythm shaped by light and darkness long before the first creature ever took a breath. This is where sleep's story begins, not with dreams or thoughts or eyelids, but with chemistry learning to sway with the turning of the world. A small, quiet pattern carried forward by every organism that would follow, from worms to whales to humans lying awake at night, wondering how something so ancient can still feel so mysterious. Long before brains learned to dream or eyelids learned to flutter, the young Earth was already a master of routine. Every 24 hours, with impeccable discipline, the planet turned its face to the sun and then away again. Light flooded the ocean surfaces, heating the waves. Darkness followed, cooling them. For the earliest multicellular life, this steadiness, the planet's slow, patient spinning, became the most reliable force they would ever know. And without realizing it, these organisms began to drift into a strange partnership with the rotating world above them. In these expanding seas, life had grown more ambitious than the drifting cells of earlier eras. Simple colonies, soft-bodied creatures, and fragile early multicellular forms now floated, grazed, and pulsed their way through the water. They were still exceedingly uncomplicated, but something had changed. They had more to lose. They needed steadier supplies of energy. They needed to avoid abrupt changes in temperature. They needed to navigate a world whose conditions changed not just by chance, but by rhythm. The sun was no longer just a source of nourishment. It was a schedule. And as day and night recurred, organisms began experimenting with ways to anticipate them. What emerged was not a conscious awareness, but a molecular choreography. Tiny clusters of proteins, pigments, and chemical regulators began responding to changes in light. Some were struck directly by photons and shifted shape. Others sensed downstream effects, heat, nutrients, oxidation, and began to oscillate. One reaction triggered the next, and slowly, these chains of chemistry arranged themselves into 24-hour patterns that matched the planet's rotation. The world had given life a cycle, and life, ever practical, started building routines around it. By this time, light meant more than photosynthesis on or photosynthesis off. Many creatures fed on drifting organic matter that rose and fell with the day. But predators, too, primitive though they were, tended to appear during daylight, when vision, or its simplest precursor, offered an advantage. Meanwhile, nighttime brought its own threats. Cooling waters that drained delicate metabolisms, reactions that slowed, and conditions that could suddenly shift. For early animals, night didn't have a clear moral alignment. It wasn't good or bad. It was simply different. And that difference mattered. In ecosystems that were beginning to show the faintest hint of structure, layers of light above, shadows below, these organisms recalibrated. They learned to adjust activity not when conditions changed, but just before they changed. A subtle but monumental shift. This was the dawn of circadian rhythms, not clocks as we think of them. Nothing ticked or talked, but chemical systems that turned on and off with astonishing regularity. Genes that expressed themselves only in the dark. Proteins that accumulated in daylight and dissipated at night. Feedback loops formed the biological equivalent of a gentle pendulum, swinging through each day with calm predictability. These rhythms didn't just react to light, they forecasted it. A quiet evolutionary agreement between the planet and its passengers. An organism with a functioning circadian rhythm could begin preparing for daylight before it arrived, stockpiling molecules needed for energy production, or positioning itself optimally in the water column. Likewise, it could brace for darkness, slowing metabolism, conserving nutrients, hunkering down in layers of water that held warmth. In a world still ruled by chance, this ability to anticipate was a small miracle. Picture one of these early creatures, a soft, translucent organism floating somewhere between sunlight and shadow. It has no idea what a day is, nor what a planet is, nor what survival means. It drifts because drifting is all it knows. And yet, buried deep within its cells, molecules begin shifting as dusk approaches. They slow, quiet, and align themselves as if listening for a distant, silent cue. When night finally comes, it is ready. Not consciously, not emotionally, but chemically. Life has learned to prepare, not just react. This subtle internal guidance became so effective that even in the absence of light, these rhythms persisted. Isolate one of these organisms in constant darkness, and its internal chemistry would continue its 24-hour cycle, as if still sensing a sunrise it could not see. This persistence is perhaps the most remarkable detail. Circadian rhythms did not rely on light. They remembered light. But while internal rhythms offered structure, they also introduced complications. Not every creature's internal timing matched perfectly with the external world. Some ran slightly fast, some slow, creating tiny mismatches. A few organisms found themselves waking up in the middle of the night, chemically ready for daytime in a world still cloaked in darkness. Evolution, of course, corrected these timing errors over generations, refining cycles like a watchmaker adjusting a delicate mechanism. And through this process, light stopped being just a resource. It became information, a message from the environment, a signal that could shape behavior, metabolism, and survival itself. The sun didn't set to be dramatic. It simply obeyed physics. But for life, that reliable rise and fall was enough to spark a quiet revolution. A new partnership with the planet was forming. Earth set the tempo, and organisms learned to dance. This chapter of life's story is quiet, subtle, and profoundly understated. No eyes yet, no real sleep, no nervous mind drifting toward dreams. Just living things syncing themselves to the comforting rhythm of a turning world. A rhythm so ancient and reliable that every creature on Earth today, from mosses to elephants to you, still carries its pulse. In the chapters ahead, these rhythms will become the foundation of sleep itself. But for now, the story rests here. In a world learning that night is not just absence, but a signal, one that shapes the entire future of life on Earth. When the first nervous systems emerged, the oceans changed in a way that was almost imperceptible at the time, but monumental in retrospect. For billions of years, life had survived through slow chemical reactions, drifting and responding only when a molecule bumped into the right spot. But now, for the first time, certain creatures possessed tiny networks of cells capable of sending signals, not randomly, not passively, but intentionally and with purpose. These were not brains, not even the beginnings of them, but delicate lattices of nerve cells spreading across soft bodies like living constellations. And with these new networks came something utterly unexpected: exhaustion. The earliest neural circuits were primitive, little more than electrical threads stitched through translucent bodies, but they allowed creatures to move with a timing that chemical reactions alone could never achieve. Suddenly, life could pulse, contract, glide, or withdraw in fractions of a second. A jellyfish-like creature could beat its bell to drift upward into brighter water. A worm-like form could flex its muscles to burrow into protective sediment. Movement was no longer a suggestion from chemistry. It was a decision made by cells specialized for action. But these new abilities came with a cost. Action required coordination, and coordination required energy. For the first time, creatures weren't simply existing. They were doing, moving, navigating, responding. And all that doing placed strain on their newly minted neural tissues. Neurons, delicate and electrically excitable, could not fire endlessly. They needed time to reset, replenish, and re-establish the gradients that made signaling possible in the first place. And so, quietly, naturally, without ceremony, the first form of neural rest appeared. Picture one of these early jellyfish-like beings drifting in the gentle sway of Precambrian waters. During the day, or during moments of increased nutrients, it contracts rhythmically, tentacles trailing through currents rich with microscopic prey. Its nerve net flashes with coordinated impulses, a tiny symphony of electricity orchestrating each movement. But after hours of activity, the signals slow. The contractions become less frequent. The creature sinks into a phase of reduced responsiveness, not deadened, not unconscious, but subdued. This was not sleep as later animals would experience it. There were no dreams, no phases, no cycles of specialized brain activity. Instead, this was something more fundamental. Neural downtime, a temporary suspension of responsiveness that allowed cells to recover from the simple demands of being active in a quickly changing world. Life had begun to move faster. The oceans were no longer filled solely with drifting chemistry. They were filled with sudden bursts of motion, tiny chases, evasions, and surprising encounters. And in this newly animated world, the ability to rest became not an indulgence, but a necessity. One can imagine how evolution stumbled into the solution. A creature whose nerve net paused briefly conserved energy. Its neural cells had time to restore their ionic balances, ensuring clear, crisp signaling when danger or opportunity returned. Those without such pauses might have suffered subtle failures, slower reactions, less coordinated movement, reduced ability to contract or escape. Over countless generations, creatures that incorporated regular periods of lowered neural activity simply survived a bit better. And what evolution rewards, it eventually shapes. Early worms, flat and ribbon-like, also revealed this emerging pattern. They moved through the ocean floor with slow undulations controlled by simple neural chains running the length of their bodies. When active, these chains fired continuously, muscles tightening and releasing in smooth coordination. But during periods of safety or after prolonged periods of feeding, their neural firing slowed dramatically. The worms became still, tucked among grains of sediment. Their awareness dimmed to the lowest setting their biology permitted. This was the evolutionary world in which the concept of pausing first appeared, not culturally, not psychologically, but biologically. These creatures did not choose to rest. Rest happened to them because it needed to. Their nervous systems could only do so much before requiring time to reset. It is tempting, perhaps, to romanticize this moment as the dawn of sleep, but that would be premature. What emerged here was not sleep, but the forerunner of it. A recognition, written not in thoughts, but in molecules, that living systems with electrical communication cannot run endlessly. A recognition that action must be countered with quiet. A recognition that even the simplest neurons learned quickly that burnout was, in a very literal sense, bad for business. These early neural pauses also began to shape behavior patterns. Creatures that rested during particular environmental shifts, such as temperature drops or nutrient scarcity, accidentally established proto-cycles. They conserved energy during unproductive conditions and resumed activity when circumstances improved. Over time, this coupling between environment, behavior, and neural recovery forged the earliest foundations of what would, many millions of years later, grow into fully coordinated sleep. But for now, in these ancient seas, we see only the simplest version. Bursts of motion followed by quiet drifting, waves of electrical firing followed by lulls, creatures whose bodies moved not in endless rhythm, but in gentle fits and pauses. Life was beginning to understand, at the cellular level, that action without recovery leads to failure, and that stillness, far from being wasted time, was essential for survival. And so the ocean floors and open waters of this era were filled with a new kind of silence, not the silence of absence, but the silence of restoration. Tens of thousands of tiny nervous systems taking tiny breaks in a world where motion was still new. The moment predators entered the world, everything changed. Life had spent millions of years experimenting with motion, sensing, and nervous coordination. But until something started hunting something else, rest had never been dangerous. It had been a quiet, natural pause, the organic equivalent of drifting into stillness because nothing in particular demanded movement. But predators altered the seascape with an urgency that no creature could ignore. In those early Paleozoic oceans, vast pale blue expanses filled with drifting plankton, soft-bodied worms, and newly minted swimmers, fear appeared for the first time. Not fear as we experience it, with emotion and interpretation, but the biological reality that something larger could suddenly end you. That the water around you, once merely a medium, could now erupt into motion with lethal intent. Predators didn't enter slowly. They arrived with teeth, gripping limbs, and the unsettling charisma of creatures built to chase. The earliest hunters were small by modern standards, but in a world where bodies were soft and nerves were newly invented, they were terrifying. Their sudden strikes made rest risky in a way evolution had never accounted for. In this transformed world, pausing too deeply or too long was no longer safe. So sleep, still primitive, still indistinct, began to adapt. Life's earliest sleepers, those jellyfish-like drifters and worm-like burrowers, could no longer afford long stretches of unresponsiveness. Their survival began to hinge not on how well they rested, but on how easily they could stop resting when the water around them stirred. The creatures that slept too deeply vanished quickly, absorbed into the diets of their more vigilant neighbors. The ones that survived did so by developing rest states that were light, fragmented, and shallow. something that could be abandoned the moment conditions changed. Visualize one of these early animals nestled in the silt. Its body is flexible, translucent, and only faintly patterned with nerve networks. When undisturbed, its neural activity drifts downward, movement slow, and responsiveness drops. But unlike in earlier eras, this quiet period is punctuated by sudden arousals, brief bursts of alertness triggered by vibrations or pressure changes in the water. Even in stillness, the creature listens. If a predator approaches, the sleeper jerks awake and burrows deeper into the sediment, or darts away using reflexes that must remain at least partially ready. This pattern, resting lightly, waking often, became the first true evolutionary compromise between the body's need for neural recovery and its need for survival. And so sleep gained its first complication: anxiety. Not emotion, again, not yet, but biological vigilance. The nervous system developed the ability to enter a state that was neither full activity nor full rest, a state in which muscles loosened but didn't fully slacken, in which senses dulled but didn't fully turn off. Essentially, evolution invented sleep, then immediately added a layer of hypervigilance, because nothing in nature stays simple for long. Some early animals took this further, developing specialized receptors that remained partially active during rest. These rudimentary sensory systems functioned like tripwires, detecting shifts in current, faint chemical cues, or the vibrations caused by approaching predators. Resting creatures could now detect danger without needing to fully awaken. This helped them maintain shallow, fragmented sleep while still benefiting from neural downtime. Others began using the environment itself to increase safety. Some burrowed deep into sand or mud before resting. Others anchored themselves to stable surfaces where ambush was less likely. Some floated upward in the water column during certain hours, rising above active predators or sinking below them. These behaviors weren't conscious strategies but evolutionary habits, patterns encoded through generations of survivors who happened to rest where risk was lowest. As predators diversified, so did the strategies of the hunted. Sleep began to occur in patches, moments stolen between feeding and fleeing. A minute or two here, seconds there, adding up across the day or night. There was no long slumber, no predictable cycle, just a life built from fragments of rest carefully placed between moments of watchfulness. It was the evolutionary equivalent of dozing with the door cracked open. Crucially, this era shaped sleep into something flexible. No longer a single universal behavior, rest became tailored to ecological niche. Some creatures rested during the dim hours when hunting was difficult for sight-based predators. Others slept in brief episodes around feeding windows. A few species began alternating between motion-rich activity bursts and motion-poor recovery periods, creating the earliest hints of behavioral rhythms distinct from day and night. What emerged from all this was not yet the sleep we know today, but its emotional silhouette. Vulnerability. Rest became something animals protected fiercely because they needed it, and something they feared because it exposed them. This delicate tension between necessity and danger would shape sleep for the rest of evolutionary history. And so the oceans of this period were filled not just with movement, but with hesitation, with creatures that paused but never fully trusted their own stillness, with bodies that rested lightly as though expecting interruption, with neural networks that practiced caution even while recovering. Sleep had become a survival strategy, a calculated risk, a moment taken only when conditions seemed stable, and even then, only reluctantly. Evolution had introduced sleep, yes, but true to form, it immediately balanced the gift with a challenge. The constant reminder that staying alive required not only resting, but resting carefully. When vertebrates entered the scene, evolution seemed to take a deep breath and say, "All right, let's get complicated." The oceans, once dominated by soft-bodied wanderers reacting to the world with simple nerve nets, now held creatures with legitimate control centers, clusters of neural tissue capable of integrating information rather than merely relaying it. For the first time, brains were becoming thinkers, not just responders. And with these new thinkers came new demands. More neurons meant more signals, more connections, more possibilities, and far more chaos if those connections weren't regularly maintained. A growing brain, it turns out, is needy. Early vertebrates, jawless fish gliding through Ordovician waters, carried in their heads small but efficient neural hubs that could coordinate swimming patterns, sense subtle water vibrations, and make swift decisions about approaching threats. Their brains had regions specialized for processing stimuli and orchestrating the body's movements with new precision. But this upgraded machinery, unlike the scattered nerve nets of earlier creatures, couldn't function indefinitely on a simple cycle of pause briefly, then resume. The new neural architecture required more thorough upkeep. These expanding networks of cells needed time not only to recover from signaling, but also to prune unnecessary connections, strengthen useful pathways, and stabilize the rapidly shifting patterns produced by more sophisticated senses. In short, vertebrate brains required maintenance schedules, preferably ones that weren't interrupted every few moments by external distractions. And so sleep deepened. Instead of shallow dips into reduced responsiveness, early vertebrates began experiencing distinct phases of rest. These weren't the fully developed sleep cycles seen in later mammals and birds, but they were structured and meaningful. During some phases, the brain quieted uniformly, as though dimming every light in the house at once. In others, certain regions pulsed with slow, powerful waves of activity, coordinating a kind of internal housekeeping that kept the brain from descending into neural disorder. For the first time in Earth's history, an animal could truly disconnect. Imagine one of these early vertebrates, a small, armored fish resting among ferns of ancient seaweed, while tiny arthropods scuttle by. Its mind, still simple by modern standards, is complex enough to demand periods of low activity, yet sturdy enough to afford deeper descent into stillness than any creature before it. This fish can remain still longer, its body supported by rigid plates that discourage opportunistic bites from passing predators. Its senses remain somewhat alert, but the brain inside them shifts into slow, rhythmic patterns, focusing inward rather than outward. This deeper rest allowed something new to happen: internal organization. Neural circuits stabilized, memory traces sharpened. Connections that had been formed during the day, perhaps through a successful escape or exploratory swim, were strengthened. Others, useless or confusing, were weakened or removed. In these early vertebrates, sleep was no longer a mere recovery period. It was becoming a sculptor, carving the brain into a more efficient machine. Of course, this luxury came with prerequisites. To sleep deeply, an animal needed the ability to survive temporary vulnerability. For vertebrates, this became possible through several evolutionary advantages. Some had bony armor that deterred many predators, granting them moments of stillness without being torn apart. Others sought shelter among rocks, reefs, or burrows, habitats offering enough protection to allow a deeper, more relaxed form of rest. A few species evolved passive defenses like toxins or camouflage, effectively buying themselves time to disconnect without becoming someone's midnight snack. The result was profound. Sleep began diverging from simple avoidance of exhaustion and becoming a strategic investment. The deeper the brain, the deeper the rest required, and the greater the payoff. Well-rested vertebrates navigated their world with sharper reflexes and better coordination. Their senses worked more effectively. Their learning, basic though it was, benefited from the internal rewiring that occurred during their deeper rest phases. And in a world where survival hinged on split-second responses and keen spatial awareness, these advantages mattered. This period marks one of evolution's most significant transitions in the story of sleep. For the first time, sleep became an active process rather than a passive one. The brain wasn't merely off, it was doing specialized tasks that couldn't be accomplished while awake. These early stages of neural oscillation set the blueprint for all later vertebrate sleep, from the slow wave cycles of reptiles to the dream-rich REM sleep that would eventually emerge in mammals. But in these early ages, such complexity was still in its infancy. Sleep was deeper, yes, but it was also primitive. There were no dreams yet, no imagery, no storylines, no replayed memories of hunting or hiding. The brain was still too simple for internal theater. What occurred during this deeper rest was structural, not imaginative. It was a kind of neural housekeeping, sweeping the floors, tightening the hinges, oiling the gears. And yet, for all its simplicity, this deeper sleep marked a turning point. With the emergence of more intricate brains, nature had stumbled upon one of biology's most powerful tools for cognitive advancement. The cost was vulnerability, but the benefits were extraordinary. Clearer thinking, better reactions, and the ability to adapt behavior from experience. Bigger brains demanded better maintenance schedules, and sleep complied, stretching into something more refined, more layered, and more essential than ever before. By the time early fish filled the Paleozoic oceans, sleep had become both deeper and more necessary. But it had also run into a new practical problem: gills. Gills, marvelous structures though they are, presented a unique challenge. Many ancient fish depended on the steady movement of water across these delicate filaments to extract oxygen, and stopping completely meant more than slowing metabolism. It meant suffocating. This limitation forced evolution into an unusual corner. Rest could no longer occur in the familiar stillness of earlier creatures. It had to happen on the move. And so, for the first time in Earth's history, animals began sleeping while swimming. Not gracefully, not serenely, and certainly not with the dreamy abandon that later mammals would enjoy. These early fish practiced a kind of half-rest, their muscles powering slow, rhythmic motions, while parts of their nervous systems dimmed. It was a compromise born from necessity, a delicate balancing act between recovery and respiration. They never fully let go. To imagine this kind of sleep, picture a fish drifting through ancient waters, the color of faded jade. Its body moves with gentle, S-shaped waves, no longer the quick, darting patterns it uses while awake. Its fins angle slightly downward, guiding it in a slow, looping trajectory. The fish appears almost serene until you realize the truth. It is neither fully awake nor fully asleep. It is suspended in a state evolution cobbled together out of sheer practicality. During these partially restful states, certain regions of the fish's brain decrease their activity, reflexes dull, responses slow. Yet motor circuits responsible for constant movement continue firing at low intensity. The fish's swimming becomes automatic, like a mechanical clock that refuses to stop ticking even as the rest of the system powers down. This is sleep as a compromise, not a luxury. And because the oceans by this time held predators of all shapes and sizes, armored fish, swift hunters, enormous jawed swimmers, sleep had to be not only partial but cautious. A fish drifting too slowly risked becoming a convenient meal. One drifting too deep risked oxygen-poor waters. One drifting too high might encounter surface dangers. Sleep in this era was an act of trust in both one's environment and one's anatomy, and neither always behaved reliably. Over generations, fish evolved strategies to make this precarious form of rest safer. Some species adopted predictable patterns, timing their restful drifts during hours when predators were least active. Others hugged the edges of reefs or kelp-like structures, swimming in slow circles around natural barriers that offered partial shelter. A few used the shadowed underside of floating debris as a moving canopy of safety. The ocean, full of shifting shapes and currents, provided countless improvisations, and fish learned to use them. One of the most remarkable adaptations was the fine-tuning of sensory vigilance. While large portions of their neural tissue rested, fish retained selective alertness in circuits attuned to pressure changes and water vibrations. The faintest ripple, a predator passing meters away, a sudden shift in current, was enough to jolt them from their semi-sleeping drift into a quick burst of self-preservation. This selective sensitivity formed a kind of early warning system, allowing fish to sleep lightly while still detecting threats. It was the aquatic version of sleeping with one eye open, except the eye in question was more metaphorical than literal. Even more nuanced was the development of variable muscle tone. Instead of shutting down completely, muscle groups entered a reduced energy state, conserving resources while still maintaining enough force to support gentle locomotion. Evolution was learning a subtle truth. Rest does not have to be immobile. Life can restore itself through controlled quietude rather than total stillness. This capacity would later influence the sleep strategies of many other vertebrates who, for different reasons, could not afford complete immobility. These drifting sleep patterns also affected how fish interacted with their environment. During these semi-restful states, feeding slowed or stopped, yet fish continued to encounter drifting nutrients. Some species evolved the ability to take in small bites or particles even while partially asleep, a kind of unconsciously opportunistic grazing. It wasn't deliberate, but it was efficient. The ocean, it seemed, rewarded creatures that could multitask, even in their least conscious moments. But perhaps the most fascinating consequence of this partial sleep was its impact on group behavior. Many early fish began forming loose schools, not for social reasons, but for safety during vulnerable periods. A drifting fish was less likely to be attacked if it was surrounded by dozens of other drifting fish, each one offering an alternative target. Over millions of years, this simple advantage contributed to the early foundations of schooling behavior. Not social bonding yet, but coordinated rest by proximity. These fish moved together, slowed together, and drifted together through half-sleep, a congregation of bodies relying on collective chance. Still, despite these innovations, sleeping while swimming was never truly relaxing. It was functional, efficient, barely sufficient. A form of rest that said, "Yes, you may recover, but do not forget where you are." Evolution, after all, doesn't design for comfort. It designs for survival. And for these early fish, survival meant staying in motion even when the body begged for pause. In this chapter of sleep's history, we see a profound truth. Rest adapts not only to the brain, but to the body that houses it. With gills requiring flow, predators requiring vigilance, and muscles requiring constant movement, sleep transformed again into something rhythmic, partial, and endlessly cautious. A living reminder that the luxury of complete stillness would only come later, in animals who finally found ways to keep breathing without moving. But that part of the story belongs to the land. And as life prepares to crawl out of the water, sleep follows it, ready to reinvent itself once again. By the time vertebrate brains reached a new tier of complexity, layered, folded, and humming with specialized regions, something extraordinary began happening in the dark. Sleep, once a simple quieting of the nervous system, transformed into a workshop of internal activity. The oceans of the Devonian and Carboniferous ages housed creatures whose brains were no longer satisfied with idle silence. When the world dimmed and the senses loosened their grip, these growing neural networks turned inward, sparking patterns of electrical murmuring that were unlike anything evolution had produced before. These early, almost dreams were not yet stories, nor images, nor emotions. They were something quieter, simpler, and far more foundational: rehearsals. Imagine an early fish or primitive amphibian settling into the bottom murk of an ancient river. Its body relaxes, its fins gently spread, and those external stimuli, current, light, motion, begin to fade from the brain's immediate concerns. But instead of shutting down completely, parts of the brain flicker in rhythmic, echoing pulses. These are not reactions to the outside world. They are reflections of what happened earlier that day. A near miss with a predator, an unusually successful chase, a new territory explored along the silty riverbank. The brain, sensing a quiet moment, begins replaying these experiences, not vividly, not consciously, but as ripples of neural impulses repeating the same pathways that fired during wakefulness. This replay strengthens successful patterns and weakens those that proved unhelpful. Movements get refined, responses sharpen, even simple choices, turn left or turn right, become more efficient the next time the creature wakes. Little by little, evolution discovers that the brain can improve itself even when the body rests. This was the beginning of dreamlike activity, neural rehearsal. These worlds teemed with creatures navigating complex environments for the first time in evolutionary history. Forests of giant horsetails and early ferns choked the shorelines, where amphibians hid in tangled roots and muddy shallows. Rivers and ponds filled with competition, fish hunting smaller fish, amphibians learning to stalk insects, predators lunging at anything that twitched. As ecological interactions became richer, the brain had more and more information to process, and sleep, with its calm quietness, offered the perfect moment for that processing to unfold. The first dreamlike states were primitive but powerful. Electrical recordings, if one had been there with a very patient time machine, would show waves of neural activity sweeping across the brain, not in reaction to the outside world, but generated internally. These were the earliest whispers of imagination, though without vision, emotion, or narrative. Just electrical rehearsal, like a musician practicing scales with no melody yet in mind. The evolutionary advantages were enormous. Animals whose brains rehearsed successful movements, even unconsciously, awoke better prepared for the challenges of the day. They reacted faster to predators, aimed more accurately when striking prey, navigated terrain more confidently, and adapted to new environmental patterns sooner. Those without this internal replay lagged slightly behind, a disadvantage that compounded across generations. Sleep, therefore, became more than a break. It became an opportunity. A training session conducted not in the physical world, but in the quiet corners of the nervous system. But as neural networks grew more intricate, these nighttime rehearsals grew more chaotic. Neurons freed from the disciplined structure of sensory input, sometimes fired in surprising combinations. Pathways that had never been activated together during waking hours suddenly intersected. A creature might experience a fleeting burst of neural coordination, representing a movement it had never actually performed. These were not dreams in our sense, but they were the first hints of something playful, a brain starting to entertain itself when the lights go out, if only by accident. And in these accidents, evolution found something useful. Unusual neural combinations can lead to creative solutions, unexpected muscle synergies, new escape behaviors, novel ways of using the environment. Even without conscious awareness, these strange nighttime rehearsals gave animals a small cognitive edge. They awoke slightly more adaptable, slightly more flexible, and slightly more capable of surviving in rapidly changing ecosystems. Amphibians in particular, living both in water and on land, benefited deeply from this emerging internal rehearsal. Their environments were dual and unpredictable. Slippery rocks, shifting mud, low branches, sudden shadows. Sleep allowed their brains to integrate information from these varied habitats, blending aquatic and terrestrial experiences into smoother, more coordinated movement patterns. Over millions of years, these internal processes became more refined. Sleep divided into clearer phases, some quiet and restorative, others active and internally noisy. During these active phases, brain waves pulsed in bursts, sometimes resembling wakefulness more than rest. But the body remained still, inhibited by specialized circuits that prevented animals from acting out their internal rehearsals. This protective immobility was essential. Without it, a creature might thrash itself into danger while reacting to signals that didn't correspond to the world around it. In this balance, bursts of neural activity constrained by muscle stillness, we find the earliest scaffolding of what would one day become REM sleep. Not yet dreams, not yet stories, but unmistakably the roots of them. These ancient brains were discovering that rest could be both reflective and inventive, that the quiet dark could be a workshop where the mind replays the past, tests the future, and dabbles in new combinations simply because the usual rules of sensation no longer hold it in place. The first dreams, if we can call them that, were nothing more than murmurs, neural flickers echoing the day's experiences. But from these flickers, a vast internal world would eventually bloom. Next, life leaves the water, carrying its fragile new sleep patterns into a harsher, brighter landscape, where rest must once again reinvent itself. When the first vertebrates heaved themselves onto land, they must have imagined they had discovered a world of endless opportunity. Air to breathe, insects to hunt, sunlight to bask in. What they did not know was that land came with its own set of complications, particularly for the delicate ritual of rest. Underwater, sleeping had been influenced by currents and predators and the need to keep gills supplied. But the land? The land added gravity, desiccation, heat swings, cold snaps, and the novel problem of, what do I do with myself when nothing around me floats? It turns out sleeping on land is harder than it looks. The earliest pioneers, primitive amphibians exploring muddy banks, shaded pools, and fern-thick forests, were the first to experience this challenge. Their bodies were still partially designed for the buoyant embrace of water. Muscles that required little effort to hold position in a pond suddenly sagged under their own weight. Lying still on land took energy, and awkwardly so. To sleep, these animals needed to find positions that wouldn't strain their limbs or collapse their chests. A poorly chosen sleeping posture could mean suffocation, dehydration, or waking up in the middle of the night only to realize gravity had rolled them into a very inconvenient patch of sun-baked soil. Temperature, too, became a relentless choreographer of sleep. Water had always moderated heat, softening day-night extremes. Land did no such favors. The forest floor could be warm in the afternoon, bitterly cold at dawn. Early amphibians learned, again through instinct and evolutionary trial, that sleeping in the wrong microclimate could be fatal. If they rested somewhere too exposed, the chill would seep into their bodies, slowing metabolism to a dangerous crawl. Too warm, and they risked dehydration, a threat far more pressing on land than in water. As a result, early land dwellers became connoisseurs of sleeping spots. Moist crevices beneath roots, shaded banks beside streams, pockets of humidity trapped under fallen logs. These became essential refuges. A good sleep site offered three basic promises: shelter from predators, stable moisture, and a temperature that wouldn't sabotage their physiology. Sleep was no longer simply a biological necessity. It was an environmental negotiation, a careful evaluation of each patch of Earth. This new need for strategic sleeping locations had consequences for the structure and timing of rest. Amphibians, unlike their aquatic ancestors, could not afford prolonged periods of stillness on open ground. Their skin dried quickly, their bodies cooled rapidly, and predators, new terrestrial ones, became more adept at spotting motionless shapes among leaves. Sleep became shorter, divided into multiple smaller bouts. Even in safety, early amphibians seemed almost restless, as if the land itself whispered, "Are you sure you want to lie here for that long?" Predators of the land, meanwhile, gained new advantages. On solid ground, sound traveled differently. Vibrations through soil could reveal the location of resting animals. The rustle of breathing against leaves, the faint shift of a sleepy limb. These gave hunters clues they had never possessed underwater. Sleep, therefore, contracted further. It became quicker, lighter, and more contingent on immediate escape routes. Amphibians likely chose to sleep near water, not just for moisture, but so they could slip back into the relative safety of a pond with a single movement. Reptiles, arriving later on the stage, refined these challenges with their own peculiarities. Unlike amphibians, they didn't dry out easily, but they did rely almost entirely on external sources of heat to regulate their bodies. This meant their sleep became tightly tied to daily temperature cycles. A reptile could not simply sleep wherever it pleased. It had to sleep where the night wouldn't drain too much warmth from its tissues. Burrows, rock crevices, underground chambers, and dense vegetation became essential. A reptile sleeping in the wrong spot might awaken so cold and sluggish that it could barely move, a condition evolution politely but firmly discouraged. Reptiles also pioneered one of the land's most effective sleeping strategies: stillness as invisibility. Many species developed coloration that matched soil, leaves, bark, or stone. This made their resting bodies harder to detect, allowing them to lengthen their sleep without increasing vulnerability. But even with camouflage, their sleep remained cautious. Their brains didn't indulge in deep internal activity. Instead, they favored quick reversibility, states that allowed immediate awakening at the slightest disturbance. This entire era of terrestrial adaptation transformed sleep into a behavior defined more by place than by timing. Where an animal slept mattered far more than when. Environmental cues, humidity, warmth, concealment, became the architects of rest. The land reshaped sleep into a mosaic of short, opportunistic windows rather than a single dependable block of time. But perhaps the most striking shift was psychological, if we can use such a term for early amphibians and reptiles. In water, sleep had been part of a gentle ebb and flow, woven into the rhythms of currents and tides. On land, sleep felt more like a pause in the face of constant risk. Every creature that settled onto solid ground carried a new tension in its biology. The conflict between needing to shut down and needing to stay alive. From this tension, sleep evolved new complexity. It became adaptive, flexible, environmental, and cautious. Many species divided their sleep into countless fragments spread across the day, each depending on shifting temperatures and the availability of safe, moist hideouts. Some slept primarily at dawn or dusk, when the world was cooler but not cold. Others rested only after storms, when humidity rose and predators were less active. And so the first sleepers on land moved through their days with a newfound sensitivity to weather, terrain, and shelter. Their nights, if they slept at night at all, were shaped not by cosmic cycles alone, but by the tactile realities of soil and air. The land had changed sleep forever. It had given animals a world rich in possibility, but demanding in its conditions. And from this difficulty, sleep grew more adaptable, more intricate, more tied to survival than ever before. In the next chapter, sleep turns minimalist as reptiles refine its efficiency, proving that sometimes less really is more. By the time reptiles fully claimed the land, sleep had already transformed from a drifting aquatic pause into a delicate terrestrial calculation. But reptiles, ever the champions of efficiency, took this calculation and reduced it to its simplest functional form. Reptilian rest became a masterpiece of minimalism, honed by cool blood, patient metabolism, and a lifestyle built on conserving energy rather than spending it. In these ancient landscapes, sleep was not an indulgence, not a complex internal exploration, but an economical maintenance routine. Just enough downtime to reset the system, and not a moment more. Reptiles carried a physiological advantage that shaped their evolution of sleep. They were ectothermic. Their internal heating and cooling systems did not run constantly. Instead, they absorbed warmth from the sun and shed heat into the environment as needed. This meant their bodies operated on slow-burning efficiency, a pace that made elaborate, energy-heavy sleep unnecessary. Where mammals would one day develop dreams and emotional processing, reptiles pruned sleep down to neural housekeeping, a kind of nightly, or perhaps even not nightly, straightening of the shelves. Imagine an early reptile resting beneath a sun-warmed slab of stone. Its heart beats with the unrushed cadence of an organism that expects the world to move at its pace. When it finally settles, its body doesn't plunge into deep, intricate sleep cycles. Instead, it slips into a shallow, steady state where neural activity decreases uniformly, but never entirely disconnects. Muscles loosen, but not so completely that escape becomes impossible. Senses dull, but stay alert enough to notice the thud of a nearby predator's step. This is sleep designed not for exploration of the inner mind, but for staying alive with a minimal energy budget. Reptilian sleep is fundamentally pragmatic. These animals rarely face the social complexities that would one day demand richer sleep architecture. They don't form emotional bonds that need nightly sorting, nor do they rely heavily on memory-based learning that requires intense neural replay. Most reptiles operate through instinct refined across generations, not through personal experience sculpted into behaviors from day to day. Their sleep, therefore, serves fewer cognitive tasks. Instead, it focuses on keeping neural circuits stable and functional, pruning unnecessary activity, and restoring depleted cellular resources. This practical approach created one of the most adaptable sleep systems in the animal kingdom. Many reptiles sleep in short bouts, scattered throughout the day or night depending on temperature, predation risk, and environmental conditions. Instead of committing to a single long block, they sleep in modular fragments, an elegant, flexible strategy shaped by an inconsistent world. A sudden drop in temperature might shorten a rest period. A warm, safe hiding spot might lengthen it. Reptiles track their energy needs and environmental cues far more tightly than creatures with warm-blooded metabolisms. Their sleep is precise, not performative. Their shelters, too, are minimalist masterpieces. A crevice beneath a rock, a hollowed tree trunk, a burrow abandoned by some unlucky predecessor. These aren't cozy beds, but functional microclimates. Safety, temperature, and humidity define reptilian sleep sites. Comfort plays no role. If a place reduces energy loss and makes an ambush unlikely, it becomes a bedroom. A rock can be a heat reservoir. A patch of leaf litter can be a disguise. A shallow pit in sand can moderate temperature just enough. Reptiles mastered the art of working with the environment rather than bending it to their needs. In this sparse framework, predators and prey both found ways to optimize rest. Herbivorous reptiles tended to sleep longer but lightly, keeping their senses tuned to danger. Carnivorous species slept shorter but deeper, relying on strength and sudden bursts of energy to compensate for vulnerability. Even giant reptiles of the Mesozoic displayed variations of this pattern, some sleeping in shaded hollows, others beneath ferns or in underground chambers, but all adhered to the same essential truth: rest just enough to maintain performance, never enough to invite catastrophe. The neural architecture of reptiles further reinforced this minimalist design. Their brains, though capable and surprisingly sophisticated in their own right, did not require the elaborate internal rehearsals or emotionally tinted cycles that mammals and birds would evolve later. The reptilian brain performs maintenance as though sweeping a room, removing clutter, reinforcing key pathways, stabilizing circuits. The work is methodical and efficient. No dramatic fireworks of internal imagery, no bursts of rapid neural storms, just steady, functional recalibration. Reptiles refined sleep into a streamlined tool, discarding the embellishments that later lineages would embrace. If sleep were a conversation, reptiles would keep it concise. Are the neurons repaired? Yes? Good. Back to work. Their version of sleep doesn't wander or elaborate. It resets, refreshes, and moves on. They perfected the art of resting without committing, closing down some systems but never unplugging completely. This minimalist sleep also affected the timing of reptilian activity. Many species became masters of crepuscular rhythms, active during brief windows of manageable temperature at dawn and dusk, resting during the extremes of midday heat and nighttime cold. Sleep folded itself into these cycles with the same efficiency governing their waking hours. A reptile might take multiple brief rests as temperatures shift, each one providing just enough neural restoration to sustain the next burst of activity. This approach proved remarkably stable. Reptiles thrived across deserts, forests, riverbanks, and mountains. Their flexible sleep habits allowed them to colonize harsh environments where other animals struggled. In places where food was scarce, their minimal sleep needs conserved precious resources. In places where predators were numerous, their light, easily disrupted sleep improved survival. As evolution continued, reptiles remained the custodians of sleep's simplest form, the version stripped down to its most essential components, a rest that restores but rarely indulges, a pause that refreshes but never fully releases its hold on the world. In the next chapter, feathers arrive, and with them one of the strangest, most ingenious adaptations in sleep's long history, the astonishing ability to rest with only half the brain off duty. When the first birds lifted themselves from the forest floor and into the sky, they inherited two great gifts: feathers and flight. Feathers promised insulation, display, and aerodynamics. Flight promised escape, exploration, and opportunity. But hidden inside these gifts was a problem evolution had not yet solved. How do you sleep when gravity, predators, cold air, and long-distance movement make rest a dangerous luxury? The sky was beautiful, but it was unforgiving. A tired fish could drift. A tired reptile could flatten itself under a warm stone. A tired bird, however, could easily fall off a branch, plummet mid-flight, or freeze in the night winds. Sleep, therefore, needed to change dramatically. Birds reshaped sleep into one of the most extraordinary balancing acts in the history of life. A life perched between worlds. The first challenge came from roosting. Unlike mammals that curl into nests or dens, many early birds slept standing, feet clasped around branches or reeds. They balanced themselves on narrow perches high above the ground, protected from ground-dwelling predators but exposed to everything else. Wind gusts, shaking branches, and the ever-present threat of something swooping silently through the dark. To sleep here required an astonishing degree of coordination. Birds evolved a locking tendon system that kept their feet clamped tight even when their muscles relaxed. A resting bird, toes curled around its perch, could sleep without falling, even when its body drooped and its head tucked under its wing. But balance alone wasn't enough. A bird completely lost to sleep would be an easy target. Something more flexible, more cautious, was needed. This is where evolution delivered its stroke of genius. Unihemispheric sleep. Half the brain sleeps, half the brain guards. Unihemispheric sleep is exactly what it sounds like. One hemisphere of the brain rests while the other remains awake, or at least alert enough to monitor the world. It is difficult to overstate how unusual this adaptation is. The two halves of the brain take turns shutting down, switching roles as predictably as the passing of the sun. One eye closes, the other remains open. One side drifts into restorative slow-wave sleep, the other listens, watches, calculates. The result is a creature that sleeps without fully surrendering. It rests while maintaining balance, guarding its surroundings, and reacting instantly to danger. The bird becomes a biological paradox, half asleep, half ready for anything. Sleeping with half a brain turned off, surprisingly effective. This adaptation was shaped not by convenience, but by brutal necessity. Early birds lived in a world where predators lurked in trees, on the ground, and in the air. They needed sleep to maintain their sharp sight, high metabolism, and rapid reflexes, but they could never afford the vulnerability that deep, total sleep would bring. Unihemispheric sleep became their solution, and it worked beautifully. Migration, the ultimate test of sleep's flexibility. Then came migration. Long-distance travel introduced problems no reptile or amphibian had ever encountered. Some birds traveled thousands of kilometers in long, punishing stretches across oceans, deserts, and mountain ranges. Landing to sleep wasn't always possible, and even when it was, stopping could be dangerous. So birds took their inventive sleep strategies to the next level. Some species learned to sleep in the air. They slept in short bursts, seconds at a time, often with one hemisphere of the brain drifting into rest, while the other monitored wing position, altitude, and the shifting winds. Certain migratory birds even timed their sleep with atmospheric updrafts. When rising air lifted them naturally, they allowed one hemisphere to fall into deeper rest, trusting physics to carry their weight. This was sleep as a moving target, fragmented, minimal, opportunistic, and yet it supported some of the most extreme physical feats in the animal kingdom. A bird crossing an ocean could accumulate enough micro-sleeps to sustain its metabolism until land reappeared on the horizon. In these moments, sleep ceased to be a destination and became a rhythm woven into the very act of movement. Cold nights and high stakes. Sleep also adapted to temperature. Birds run hot, much hotter than mammals, and maintaining this heat through the night is expensive. During sleep, their metabolic rate drops, but not too much. Otherwise, they risk hypothermia. To manage this precarious balance, birds evolved a sleep posture that minimizes heat loss. Many tuck their heads under their wings, trapping warmth, reducing exposed surface area, and aligning feathers to seal in heat. Others fluff their plumage into insulating balls, creating pockets of warm air against their skin. Even sleep duration adjusted to temperature. On cold nights, birds sleep more fitfully, waking often to generate heat. On warm nights, sleep deepens slightly, allowing for longer periods of uninterrupted rest. Sleep had become not just a neural requirement, but a thermal calculation. Brain design shapes rest. Bird brains differ structurally from mammal brains. Though highly capable, their architecture supports shorter cycles and lighter sleep. This makes unihemispheric rest even more effective. Birds never sink into long, indulgent dream phases. Instead, sleep comes as a mosaic of tiny segments, each tailored to immediate needs. Some periods involve neural repair. Others enable memory consolidation, especially crucial for birds that navigate long distances or learn complex songs. But every function is trimmed to its essentials. Bird sleep packs an extraordinary amount of cognitive maintenance into incredibly small time frames. Efficiency becomes the guiding principle. The elegance of restraint in all of this. Birds revealed a new truth about sleep. It can be both fragile and astonishingly resilient. It can exist in fragments, in motion, balanced on narrow branches or drifting above oceans. It can adapt to cold, to danger, to the demands of migration and vigilance. It can divide itself, one hemisphere at a time, without losing the essence of its purpose. Birds turned sleep into a flexible art form, not deep, not indulgent, but brilliant in its adaptability. In the next chapter, mammals will take a very different path, diving inward, deepening sleep into something emotional, restorative, and filled with the beginnings of dreams. When mammals first emerged beneath the canopy of ancient forests, they carried with them a quiet revolution, not in claws or teeth or speed, but in how they rested. Their new bodies, warm-blooded and fur-clad, entered the world with an ability no reptile, amphibian, or early fish had mastered: the capacity to sleep deeply and safely for long stretches without depending entirely on the environment's whims. Warm-bloodedness was more than a fancy metabolic trick. It freed mammals from the temperature constraints that had ruled reptilian sleep. A mammal didn't need the sun to warm it before the mind could function, nor did it need to wake at every breeze to avoid freezing. Its internal furnace burned continuously, and though this required vast amounts of energy, it also created stability, a rare commodity in the ancient world. With this stability came an unexpected gift, the chance for the brain to wander inward. Fur, warmth, and the first comfortable sleepers. Fur, too, changed everything. Where reptiles had to pick shelter based on temperature, mammals could rely on their own insulation. A bit of moss, a hollow trunk, a burrow, or a pile of leaves could suddenly become a soft refuge. These simple comforts made longer sleep more feasible. The world outside remained dangerous, but mammals could curl into themselves, wrap tails over noses, and drift into something deeper than any creature before them. And parental care, another mammalian hallmark, allowed group sleeping, synchronized rest, and the reassurance that someone was always alert. In a litter, some pups would stir while others slept, creating a natural cycle of safety. For the first time in evolutionary history, an animal didn't need to be entirely responsible for its own survival during sleep. Care gave mammals permission to let go. Evolution didn't invent fur just for warmth. It wanted better naps. Inside the mammalian mind, a new kind of night. With these conditions in place, mammalian sleep blossomed into something astonishingly complex. Sleep phases became distinct. Brains of early mammals didn't simply quiet down. They shifted gears, entering alternating patterns that reflected two very different internal worlds. The first was slow-wave sleep, a deep, restorative state where neurons fired in broad, rolling waves, like the steady breath of a resting giant. During this time, the body repaired tissues, bolstered the immune system, and reset hormonal balances. Muscles relaxed fully, the heart slowed, and the brain sank into a quiet so profound that even strong disturbances sometimes failed to wake the sleeper. But then came something far stranger: the birth of REM sleep. At intervals, the sleeping mammalian brain erupted into a flurry of rapid, chaotic, intensely coordinated activity. Neurons fired as though the animal were awake, sometimes even more actively, but the body remained almost entirely still, held in place by inhibitory systems that prevented movement. Eyes flickered beneath lids in quick, twitching arcs. Breathing became irregular, shallow, sometimes nearly hurried. This was the dawn of REM sleep. No other lineage before mammals had experienced anything quite like it. Bird sleep was efficient and strategic. Reptile sleep was shallow and functional. Amphibians and fish slept mostly to avoid exhaustion. But mammals? Mammals developed a kind of internal rehearsal hall where memories were revisited, emotions sorted, behaviors processed, and experiences woven into deeper understanding. REM sleep wasn't simply rest. It was learning. It allowed mammals to consolidate experiences into long-term memory. Young mammals, endlessly curious and often reckless, benefited especially. Their REM sleep ran longer and more frequently than adults, sculpting their brains at breathtaking speed. A newborn mammal's nights were filled with neural storms, wild with synaptic refinement. Some scientists like to describe REM as the brain dreaming itself into competence. In early mammals, this was literal. They awoke sharper, more coordinated, more socially aware, better at navigating their environments. The nighttime became a training ground. The emotional layer, what made REM sleep even more distinctive, was its link to emotion. Mammals, unlike their scaly predecessors, developed richer emotional lives: fear, attraction, playfulness, attachment. These emotions needed tending. They left marks on the mind that required sorting, smoothing, sometimes softening. REM sleep helped regulate these inner storms. When a primitive mammal faced a predator, lost a littermate, or bonded with its kin, the emotional weight of these events didn't simply fade. At night, REM sleep reprocessed them, ensuring that traumas didn't destabilize the animal's behavior and that bonds were reinforced through memory. This connection between sleep and emotional resilience would become one of mammals' greatest biological advantages, preparing them to navigate complex social systems in ways reptiles never could. Burrows, nests, and the architecture of safety as mammals radiated into new niches, Forest canopies, underground tunnels, rocky outcrops, and sprawling plains. They took sleep with them, adapting it to each environment, but always preserving its depth. Burrowing mammals created warm, protected dens. Arboreal species built nests or found hollows where wind and rain couldn't intrude. Even early grazing mammals slept in groups for warmth and safety, arranging themselves so that at least one member remained semi-alert, echoing the protective instincts of their earliest ancestors. These shelters allowed mammals to indulge in longer cycles of sleep and richer phases of REM. Protected by numbers, fur, and warm bodies huddled together, many species could enter fully vulnerable states, something birds seldom risked and reptiles rarely attempted. Sleep as rehearsal. Innovation. Mammals became masters of trial and error learning, often inventing solutions instinctively. Their brains practiced behaviors at night without needing to perform them physically. A young mammal could practice fleeing, climbing, grasping, or navigating in the safety of sleep, rehearsing movements that would be essential by morning's first light. This internal rehearsal hall laid the groundwork for problem-solving, creativity, and flexible intelligence, traits that would become hallmarks of mammals from tree shrews to primates. The new face of rest. As mammals spread across the continents, sleep deepened, diversified, and anchored itself into the architecture of the mind. It was no longer simply a maintenance routine. Sleep became a theater of learning, a sanctuary for emotion, a sculptor of memories, and a silent rehearsal stage. Warm-blooded bodies had bought the privilege of deeper rest, and mammals used it brilliantly. Next, dreams themselves expand, as the emotional and imaginative landscapes of sleep grow more vivid, and nighttime becomes a world with its own stories to tell. By the time mammals had diversified across forests, plains, and underground burrows, their inner worlds were no longer simple spaces of instinct and reaction. Deep within their brain, structures devoted to emotion had blossomed, regions capable of processing fear, nurturing attachment, forming social bonds and recognizing patterns that stretched beyond immediate survival. The mammalian mind had texture now: hope, hesitation, excitement, anxiety, curiosity. With this growing emotional complexity came a profound shift in nighttime experience. Dreams learned to feel. Sleep had already evolved into a realm of memory sorting and rehearsal, but now emotions seeped into the edges of these nocturnal processes, coloring them with shades of experience unlike anything seen in reptiles or birds. Instead of purely replaying daytime events, the mammalian sleeping brain blended memory with mood, instinct with imagination. The result was a kind of quiet, emotional workshop, a place where feelings were rehearsed, refined, softened, and sometimes challenged. Where emotion takes root in the mammalian brain, structures such as the amygdala, the region handling threat perception and emotional significance, became deeply intertwined with sleep. During waking hours, the amygdala sounded alarms, flagged important experiences, and stamped certain memories with emotional weight. But during REM sleep, when consciousness dimmed and the mind roamed freely, this region remained surprisingly active. It fired signals not as reactions to real dangers, but as responses to remembered ones. Emotion, untethered from the immediate world, drifted through the brain like sparks from a distant fire. This gave dreams a new quality. They felt real, even though they were constructed from fragments of memory and imagination. A small mammal sleeping in its nest might relive a chase from earlier that day, not in perfect detail, but through a haze of emotion and instinct. The fear was softened by the safety of sleep, yet the memory was reinforced. When such an animal awoke, it was often better prepared to respond to danger. Its brain had practiced not the event itself, but the emotional logic behind survival. Even evolution couldn't stop the occasional bad dream. The rise of the nightmare and its purpose. Nightmares may feel like evolutionary nuisances, but they likely offered benefits long before humans existed. In the early mammalian world, full of predators, unstable food supplies, and complex social interactions, fear was not an occasional visitor, but a daily companion. REM sleep provided a controlled environment where fear could be confronted without immediate consequence. A nightmare allowed the brain to simulate threats, testing and refining reactions. It was not punishment, it was preparation. Terrifying dreams gave early mammals practice in managing overwhelming emotions, preventing panic during real-life crises. In a sense, nightmares were emotional fire drills, training the ancient brain to remain coordinated even under stress. Not every dream was dark, of course. Many were playful, reflecting the importance of exploration in young mammals. Play, a behavior strongly tied to learning, bled into sleep as well. Dream chasing, dream leaping, dream tumbling. These were simulations that helped shape the coordination of young bodies and sharpen instinctive responses. A juvenile mammal that practiced coordination in dreams could navigate the world with greater confidence during waking hours, blurring the boundaries of experience. As mammals gained more sophisticated senses and emotional responses, their dreams grew richer and more peculiar. They blended memories from different times. They stitched together recent events with distant ones. They exaggerated sensations and bent logic. A mammal might dream of a predator larger than anything it had ever seen, or of food it had never tasted, or of social interactions replayed with emotional intensity rather than accuracy. This blending wasn't a flaw, it was a feature. By mixing experiences, the brain tested relationships between ideas and feelings. It explored possibilities without risk, stitched together patterns hidden in the randomness of daily life, and strengthened associations that proved useful. Dreams became a space where creativity was born from emotion, not reason. In the safety of REM sleep, emotional processing could occur without physical consequences. A memory that frightened an animal during the day might be softened at night. A social conflict could be mentally rehearsed until it made sense. The brain didn't merely store experiences, it interpreted them. Social minds, social dreams. As mammals became more social, living in clans, colonies, packs, or herds, dreams took on additional layers. A mother dreamed of her young, strengthening attachment. A social mammal rehearsed recognition of group members. Conflicts and alliances played out in nocturnal simulations, helping the animal navigate relationships more smoothly in daylight. Emotional intelligence, still in its evolutionary infancy, found nourishment in the strange theater of REM sleep. A young mammal learning to live in a group needed more than physical reflexes. It needed the ability to read moods, anticipate aggression, and recognize subtle cues. Dreams provided a safe rehearsal space for these delicate skills. While the dream world may have been chaotic, its emotional lessons seeped into waking life in ways that shaped survival, the growing depth of night. Over time, mammals came to rely on emotionally tinted REM sleep as much as on deep restorative stages. These emotional dreams balanced the pressures of life, smoothing edges that could otherwise interfere with survival. They provided clarity to experiences that were too overwhelming, too fast, or too complicated for the waking mind to fully digest. Dreams became not just reflections of the day, but reinterpretations of it. Stories built from memory, instinct, and feeling. They taught mammals not just how to move or react, but how to cope, bond, and adapt. The dream was no longer a simple replay, but an emotional conversation between the brain and itself. This new form of sleep was a turning point. It allowed intelligence to grow, social ties to strengthen, and emotional stability to flourish. In the next chapter, as mammals band together and form communities, sleep becomes a shared experience, shaped not just by biology, but by the safety that numbers provide. Long before humans shaped nights with firelight and story, the ancestors of social mammals discovered something subtler and far older. Sleep becomes safer when shared. In the deepening forests, grasslands, and high canopies of the Cenozoic era, the solitary sleeper remained exposed, vulnerable to predators and environmental shifts. But groups, packs, herds, troops offered a different rhythm of life. With many bodies watching, resting, and moving together, nighttime became less a private risk and more a communal strategy. As mammals began forming coordinated groups, sleep changed again, quietly but profoundly. The rhythms that once belonged to individuals now echoed across families, packs, and early primate clans. The act of resting became a collective behavior, stitched into the fabric of social life. From lone sleeper to shared slumber social, sleep didn't emerge all at once. Early mammals were cautious. They tolerated the presence of kin, perhaps nestled close only during harsh weather or dangerous nights. Over generations, proximity became routine. Mothers slept with their young, forming the earliest nuclei of shared slumber. Siblings huddled near each other. And slowly, species that hunted or traveled together began resting together as well. The benefits were immediate. A group could share the burden of vigilance. One individual stirring or shifting subtly alerted the rest. Even during deeper phases of sleep, mammals were never entirely cut off from one another. The rustle of fur, a quiet grunt, the soft scrape of movement. These sounds became nocturnal signals. They conveyed safety, or on rare occasions, danger. In this way, the group functioned like a single organism, connected by the low hum of shared rest. Safety in numbers also means snoring in numbers. The evolutionary magic of a sleeping group. Sleeping together wasn't merely convenient. It reshaped survival dynamics. When mammals slept alone, they chose sheltered crevices or hidden burrows to avoid predators. But groups allowed bolder resting sites. Packs of early canids could sleep in open areas, knowing that even if some rested deeply, others would remain lightly alert. Hoofed mammals on plains could lie down in a ring, each animal positioned so that predators approaching from any direction would be noticed. Early primates could sleep in groups high in trees, using their combined presence to deter nighttime threats. This shared vigilance allowed longer, deeper sleep. Animals gained more time in restorative and REM-rich phases, the kinds of sleep linked to learning, emotional processing, and physical recovery. Group life amplified this advantage. With more rest came sharper instincts, healthier bodies, and better coordination. Over evolutionary time, species that slept communally often gained complex communication systems, improved social awareness, and more fluid group cohesion. Sleep was no longer something that happened in isolation. It became a quiet training ground for social intelligence. Synchronized rhythms. A group breathes together. When mammals began sleeping together, their biological rhythms began subtly aligning. Hormone cycles like melatonin, cortisol, and oxytocin began drifting into synchrony, influenced by shared cues, sunset, temperature shifts, audible movements within the group, even the warmth of bodies pressed together. This synchrony mattered. Animals that awoke together could forage together, migrate together, and defend themselves as a coordinated unit. Group members learned, unofficially, to follow each other's cues. When one opened their eyes, others stirred. When one settled, the rest relaxed. A shared circadian rhythm became part of the group's identity. Even dreams may have been affected. While no creature broadcasted its dreams aloud, the emotional climate of the group, the collective anxieties, the day's experiences, the social tensions, likely shaped the dreams of individuals. Dream states processed emotions not just of personal survival, but of group dynamics. In early primates especially, REM sleep may have reinforced social memories. Who groomed whom? Who offered comfort? Who asserted dominance? Who initiated play? Through these emotional dreams, bonds deepened. Comfort, bonding, and the gentle weight of another's presence touch became a powerful element of social sleep. Many mammals rested in physical contact, huddling, leaning, nesting. The warmth of a companion not only conserved heat, but calmed the nervous system. Oxytocin, the hormone of bonding, flowed abundantly in such close quarters. Sleeping together strengthened trust, and trust strengthened sleep. This mutual comfort supported the young most profoundly. Infants sleeping against a parent learned safety long before they understood the world around them. Their breathing synced with their caregiver's rhythms. Their tiny bodies warmed by shared heat. Their developing brains benefited from a steady environment, where emotional security was as abundant as milk. In early primate groups, the sleeping clusters resembled woven networks of bodies. Mothers held infants cradled in forelimbs. Juveniles draped themselves across siblings or cousins. Older individuals nestled at the periphery. The troop slept as a single, interconnected organism, each heartbeat adding to the collective quiet. Territories of trust. As social mammals spread across varied landscapes, groups began selecting habitual sleeping locations. Dens, ledges, clearings, or tree branches that became communal beds. These places gained meaning. They were revisited night after night, marked by scent, defended fiercely, and known across generations. The sleeping site became a symbol of unity, home not because of walls, but because of shared vulnerability. This dependence on group sleeping sites encouraged cooperation. Disputes were often resolved before nightfall because conflict during rest was dangerous for everyone. Social harmony became an adaptive advantage. Troops and packs that settled disagreements more smoothly slept more soundly. Those who slept more soundly performed better while awake. And so sleep subtly sculpted social structure. The social brain strengthens. Nighttime became an ally in the evolution of social intelligence. As emotions intensified and memories grew richer, sleep became a nightly sorting of group experiences. Who offered support today? Who showed aggression? Who shared food? Who could be trusted tomorrow? Dreams, feelings, and sleep cycles sharpened these distinctions. Group-living mammals awoke better prepared to navigate their social world. The group had become more than a collection of individuals. It had become a shared consciousness, lightly connected through the rhythms of communal rest. In the next chapter, sleep enters human territory, where imagination, worry, creativity, and culture all begin reshaping ancient patterns into something both familiar and astonishingly complicated. When the first humans appeared on the savannas and forest edges of Africa, they carried within their skulls one of evolution's most ambitious experiments, a brain capable of imagination, foresight, language, planning, empathy, and memory layered on memory. It was a brain that could think in symbols, dream in colors, remember danger with exquisite detail, and speculate about what tomorrow might hold. And all of this extraordinary power lived atop an ancient, fragile sleep system that had never been designed for such mental intensity. Sleep, suddenly, had a scheduling problem. For millions of years, mammals slept trusting darkness to limit activity. Night was a natural curtain that quieted the world. But humans changed everything when they learned to borrow a piece of the sun. Firelight, flickering amber and gold, did not just warm early humans or keep predators at bay. It transformed their relationship to night itself. Shadows danced, sparks rose, and faces glowed in circles of communal warmth. In those circles, people talked, imagined, remembered, warned, and invented. Night became alive with thought. Fire, the light that stretched the night. The glow of fire allowed early humans to stay awake long after other animals had retreated into sleep. Under this light, social bonds strengthened. Stories evolved, first as warnings, then as shared memories, and eventually as myth. These nighttime gatherings created something no previous species had experienced: purposeful wakefulness. The cost? Sleep had to squeeze itself into the leftover hours. Once darkness dictated bedtime, now storytelling did. Fire bought humans precious safety from nocturnal predators, lions, hyenas, leopards, but also encouraged minds to stay alert, turning over ideas, replaying the day, wrestling with possibilities. The human brain, now brimming with creativity and concern, did not shut down easily. Evolution built humans for sleep, then gave them anxiety, the hypermind. Arrives at night the human brain's greatest strengths: anticipation, imagination, curiosity, became its nighttime troublemakers. A rustle in the grass might mean nothing, or it might mean danger. The mind explored both. A memory of conflict with another group member played itself again and again, searching for meaning. A future hunt was rehearsed mentally before dawn's light. The brain didn't simply quiet at night. It processed, analyzed, speculated, and worried. Earlier mammals dreamed emotionally, but humans carried entire narratives into sleep. These weren't fragments of instinct. They were sprawling inner landscapes woven from language, memory, and creativity. And while dreams still offered emotional processing, the transition into sleep became more complicated. The mind was often too lit with thought to surrender easily. A new kind of vigilance. Humans also slept in environments that demanded unusual caution. No burrows, no thick fur, no speed that matched predators. Instead, humans relied on group structure, firelight, and rotating watchfulness. Communal sleeping became essential. Bands slept close, often huddled for warmth, noise, and reassurance. But even in groups, humans rarely slept as deeply as their mammalian ancestors. Their sleep became segmented, light dozing woven with deeper phases. Someone in the group always stirred, always shifted, always listened for danger. This constant, low-level vigilance seeped into human sleep architecture, especially across evolutionary time. Light sleepers survived. Heavy sleepers did not pass on their genes quite as effectively. Dreams become stories. Human dreams expanded beyond the emotional rehearsals of other mammals. Thanks to language and imagination, dreams sometimes formed structured plots, chases, conversations, catastrophes, strange encounters with people and landscapes twisted into surreal forms. The human dream became a place where symbols replaced instinct, where memories mingled with invention, and where emotional processing gained narrative structure. A dream might retell a hunt with exaggerated danger. It might replay a dispute with symbolic imagery. It might mash together distant memories into entirely new scenarios. Human dreams became stories that the brain used to navigate not just survival, but social complexity, emotional nuance, and identity. Nightmares gained emotional depth, not just fear, but guilt, longing, or grief. And while unpleasant, these nocturnal anxieties sharpened awareness of threats, reinforced social understanding, and prepared humans for conflicts within and outside the group. Sleeping in a landscape of predators, the African night was filled with sounds, rustling grasses, distant roars, the shrill cries of nocturnal birds. Humans had the intelligence to recognize the meaning of these sounds, and this knowledge made their sleep both safer and more restless. People developed sleeping sites with strategic advantages, high on rocks, in caves beneath shelters, or within rings of fire. These places became the earliest shared sanctuaries, chosen for collective protection. Still, human sleep remained lighter than that of many mammals. It needed to be. Survival demanded it. The birth of anticipatory consciousness. As human cognition expanded, something new crept into the night: anticipation. Humans didn't just react to danger, they imagined it before it happened. They expected scarcity, predicted storms, worried about social tensions, and planned hunts far in advance. When this anticipation spilled into nighttime, sleep became mentally crowded. Thoughts lingered past dusk. The mind paced itself in circles, revisiting the same concerns. In a sense, insomnia was born alongside imagination. The same neural machinery that created art, tools, rituals, and language also created late-night brooding. The human brain had become too powerful to fully silence. A new balance between thought and rest. Yet despite these complexities, sleep remained vital. Deep sleep restored bodies after long treks and hunts. REM processed intricate social relationships. Light sleep maintained survival. The human sleep cycle became a delicate trilogy of restoration, creativity, and vigilance, an ever-shifting negotiation between biology and thought. As societies grew, so did nighttime structure. Shared fires, predictable rhythms, roles for nighttime watchers, early forms of bedtime rituals. Sleep intertwined with culture, shaping and shaped by it. In the next chapter, this ancient story arrives in the present day, where sleep remains an evolving dance, caught between biology millions of years old and a world that changes faster than any species ever prepared for. Sleep has traveled with life for billions of years, following creatures across oceans, continents, forests, deserts, and finally, into the flickering glow of modern civilization. After all this time, after gills and feathers, burrows and tree nests, REM storms and careful communal rest, sleep is still changing. It is not a finished invention, not a perfected system, but a living, adaptable process evolving alongside every environment, culture, and species that depends on it. Even now, as the world blazes with artificial light and hums with the noise of constant activity, sleep remains what it has always been: a quiet, nightly negotiation between biology and circumstance. The fragility of an ancient rhythm. For all its resilience, sleep is astonishingly fragile. This vulnerability is woven into its nature. Sleep happens in the shadows, requiring trust, shelter, and stability. When the world shifts, ecologically, technologically, socially, sleep shifts with it, sometimes reluctantly, sometimes awkwardly, always imperfectly. Human sleep, perhaps more than any other creature's, reveals this fragility. Our brains still carry the circuitry of ancient rhythms, built for starlight and temperature cycles, for safety in groups, for darkness that signaled rest and daylight that signaled movement. Yet our environment no longer follows the same rules. Lights don't dim with dusk. Sounds don't quiet at sundown. Life no longer holds a predictable rhythm. The environment that shaped human sleep for hundreds of thousands of years has vanished almost overnight, replaced with a world of clocks, obligations, and glowing screens. And so human sleep changes, sometimes shrinking, sometimes fragmenting, sometimes stretching across odd hours. Even the notion of sleeping in one long block, 8 hours uninterrupted, is more cultural expectation than biological law. Many traditional societies sleep in 2 or more segments, with wakeful intervals of calm reflection or quiet conversation. Other cultures nap in midday heat, syncing rest to climate rather than clock. Sleep is not rigid. It bends, reshapes, adapts. A planet that never turns off. Artificial light is now one of the most powerful evolutionary forces shaping sleep. For billions of years, darkness was a universal cue. Now, we hold our own miniature suns, bulbs, screens, devices, extending the day indefinitely. To ancient biology, this is confusing. The body expects darkness to mean safety and stillness. But modern life insists that darkness often means productivity, entertainment, or distraction. The tension doesn't erase sleep, it simply changes it. Bedtimes drift later, internal clocks slip out of sync. Dreams grow more chaotic or shallow. Some people feel as though their minds refuse to wind down, a sensation unknown to our ancestors, but common now. The very flexibility that allowed sleep to survive through mass extinction, climate shifts, and radical evolutionary transitions also allows it to bend under modern pressures. Sleep has endured asteroid impacts. It will endure the smartphone. Culture, the new landscape of sleep. Long before technology arrived, culture itself had begun reshaping sleep. The earliest human groups developed rituals, rhythms, and expectations that influenced when and how they rested. Some communities slept in rotating shifts to guard against danger. Others slept more deeply in communal shelters. Over generations, cultural habits became so deeply learned that they shaped sleep architecture itself. In the modern world, expectations about productivity, work schedules, and social norms exert even greater influence. Some societies prize long nights of rest. Others celebrate short sleep as a sign of grit or success. The meaning placed on sleep, whether it is valued, dismissed, protected, or interrupted, filters into biology. The mind adapts to the cultural messages it receives, and sleep adapts with it. This interplay between culture and biology reveals a truth often overlooked. Sleep is shaped as much by the stories a society tells as by the genes it inherits. Evolution in real time. Though evolution is often imagined as a slow and ancient force, sleep shows us that biological adaptation can continue across surprisingly short timescales. In urban areas, people and animals alike develop altered circadian patterns influenced by constant light, noise, and irregular schedules. Birds living in cities sing earlier. Mammals forage later. Humans shift their rhythms to match technology, social obligations, or round-the-clock work. In quieter environments, forests, rural landscapes, communities closer to natural cycles, sleep often retains its older patterns. Earlier nights, deeper phases, more stable rhythms. Variation in sleep across populations is not a malfunction. It is evolution experimenting, adjusting, feeling its way toward new equilibria. Sleep is not static. It is a moving balance between need and environment. The brain's nightly work continues. Even in this changing world, sleep continues its ancient internal labor. Dreams still knit together emotions. Deep sleep still repairs tissues, strengthens immune responses, and resets the brain's metabolic machinery. REM still stirs images, fears, hopes, and memories into their nightly kaleidoscope. Inside each sleeper, something ancient continues faithfully, unbroken since life first learned to rest. Perhaps this is the most remarkable part of sleep's story. No matter how much the world changes, the inner logic of sleep persists. It remains essential, though its shape shifts. It remains powerful, though its environment challenges it. It remains mysterious, though science edges closer to understanding. Continuity, not conclusion. This journey through the evolution of sleep does not end with a final answer. Sleep is not finished. It evolves with every species, every environment, every new challenge. It remains flexible yet fundamental, fragile yet enduring. A biological paradox that has weathered everything Earth has thrown at it. Sleep has survived the rise of predators, the leap onto land, the emergence of flight, the invention of warm blood, and the dawn of human imagination. Sleep has survived ice ages, volcanic winters, atmospheric upheavals, and 5 mass extinctions. Sleep isn't worried about your to-do list. As long as life continues, sleep will continue with it, quietly shaping minds, bodies, memories, and dreams one night at a time.